Hello. So we're going to be going over problems 12, 13, 14, and 15 for the EE301 12-week review packet. So these problems all concern this graph shown, so we're going to be referencing it throughout the problem. The first one is just seeing, for number 12, is seeing if you understand the different properties of a sinusoid using the graph. So what we're going to do is we're going to take a look at it. We're going to have these side by side so that you can see them. And the first question asks, what is the period of the waveform? So the period is pretty easy to determine. We just look at where it starts at 0, and then we look at where it repeats itself. So that would be here at 5 seconds. So you can see the waveform reaches its original point and then starts again. So that's 5 seconds. And actually, if you look here, the time is in milliseconds. So the next one, the frequency. So from your equation sheet, you should know that frequency is 1 over the period. So that would make it 1 over 0.005, which is 200, and frequency is in hertz. So that's 200 hertz. The next one, C, is what is the time difference, delta T, between the VS and VR. So as you can see, they're marked here and here. So we can say, we'll take a look at this one, and we'll take a look at this one, and we'll say, this one looks like it's roughly at, we'll say this, so this one here is at 6.25, so we can say this one's probably at 6.5. So we'll say that's roughly equal to 7.5 minus 6.5, which would give us about 0.5 milliseconds. It's okay to estimate that kind of thing. If you're off by a little, it's not the end of the world. The next one would be to find the phase difference. On the sinusoid portion of your AC equation sheet, you'll see that the phase difference, delta theta, is equal to delta t over the period. So that would be 0.5 milliseconds over 5 milliseconds. And then that's times, my apologies, times 360 to convert to degrees. So that would give you roughly 36 degrees. Write a function for source voltage. So now we have all the elements we need. Remember, the sinusoid equation would be Vs. That would be its peak value, Vs at the peak, times the sine of 2 pi f t plus theta, which is its original angle. So its original angle is going to be, since we're going to be using Vs as the reference, is going to be 0. So that means that we find its peak value, which is, if we look over here, 6 sine of 2 pi 200. Remember, 200 was our frequency value, t. And then that would be plus 0 because it is the reference that we're using. Oh, my apologies. That is the reference that we're using. So 6 sine of 2 pi 200 t. Next, we'll express the source voltage in phasor form. Remember, this is the same as the other problems. We just take this and we're going to divide it by radical 2. And it'll be at the angle, remember, which is 0 in this case. So that's 6 over radical 2, which is roughly 4.2. And that's a 0. Now, for G, we'll use VR. So as you can see, it's a little bit off in phase, but we have the change in angle to tell us how different it is. So write a function. So remember, it's the same way. It's going to be VR of t equals VR peak times the sine of 2 pi f t plus its angle, the angle of VR. So that's its peak value, which is going to be roughly 3. The sine of 2 pi F, which is 200, T. And then the question is it positive 36? Because remember, 36 was our phase difference between it and the reference voltage. VS is our reference voltage. And if we can see here, it is 36 degrees behind, okay? Because this is the point where this crosses the 0, and then this crosses afterwards. If it crosses later, that means it's behind, which would mean this is negative 36, okay? If this curve crossed the 0 like this and was before, then you would say it was positive. But because it doesn't, it's negative. So that would mean negative 36 degrees, and that would be our equation for that one. The next problem asks us to put that same equation in phasor form. Remember, again, we just have 3 radical 2 at an angle of now negative 36, which gives us roughly 2.1 at an angle of negative 36 degrees. So since we know VS and VR, which is voltage across, find the voltage across the load. Okay, remember we're given this circuit right here at the bottom as a reference. So now that we know all of this, all we have to do is use Kirchhoff's voltage law to find the rest. So we'll draw KVL through this circuit, and we'll say 0 equals VL plus VR minus V source. And we'll rearrange to say VL is equal to V source minus VR. That gives us 4.2 minus 2.1 angle negative 36, which gives us roughly 2.81 at an angle of 26.38 degrees. And that would be our load voltage. Now it wants us to find the load impedance. All right, so our first step, or the easiest way to do it would be to find the current going through the load, and then we can use Ohm's law. All right, so the first step would be to take the resistor's voltage, right? You can use Ohm's law, and we know that if we divide that by the resistor's resistance or its impedance, which is the same value, right, we will get its current. So that is 2.1 angle negative 36 over 2. And that'll give us 1.06 at an angle of negative 36. So now that we have the current through the resistor, if you look at the resistor and the load on this circuit right here, you'll notice that they're in series, which means that the same current flows through both of them. So if I want to find Z of the load, all I have to do is take the load's voltage and divide it by that current, the same current that flows through the resistor. So that would be 2.81 angle 26.38 divided by 1.06 angle negative 36. And that's going to give us roughly 2. Oh, my apologies, not 2. Yeah, actually that is right. 2.65 angle 62.38 degrees. And this part is just normal AC analysis. Now that we've extracted all the values out of the circuit, this becomes a fairly simple AC analysis problem. The biggest challenge for this was originally finding all these values using the graph. Your last one is going to be, actually, before we move on to problem 15, they wanted to know if it's inductive or capacitive. So that's the question. That's a good question for you. Remember, we use Eli. So in this case, we have a load. We could actually do this multiple ways. We have the current being negative, and we also have the load impedance with a positive value, that would mean that because it's a positive angle, that would be inductive. So it is inductive. Or positive impedance angle means inductive. You also know that it's inductive because the current angle is more negative than its voltage angle. Remember Eli the Iceman. Lastly, draw the load equivalent circuit below. So all we have to do is take that load value, and so that's 2.65 angle 62.38. And what we'll do is we'll take that and we'll put it in our calculators. So you can just type that. If you don't know how to convert to rectangular in your calculator, just type that in with the angle, so 62.68. And then what we'll do is we'll take that, we'll press second complex, and we'll go straight to the A plus BI format, and we'll click it. And that will give us 1.23 plus J 2.35. And now we have the real component and the inductive component, the imaginary component. So all we have to do is redraw the circuit. Here's our source. There's that resistor we had at the bottom, 2 ohms. And for here, what we'll do is we'll place the load box with a resistor and an inductor. This resistor has that real value, 1.23. This inductor has the imaginary value, J 2.35. And this source still has the same source value, which was like 3, what was it like? It was like 4.2 angle 0. And that's it. That's problems 12, 13, 14, and 15.